So in that first concept question, number 7 is asking you about how do we know that the Riemann sum, when it converges, actually converges to the area between those curves. And what I was trying to get at was something a little bit deeper than what you would kind of say at first glance. I think most people just have this loose idea that, well, the norm of the partition's shrinking, so everything becomes better and better at the approximation. Well, that's kind of the rough idea, but the problem is it doesn't always work. So there are going to be situations where the Riemann sum will converge to something, but it's not the area between the curves or the work or fluid force or whatever application you're doing. And so in the answer key for the test, I reference you back to chapter 5, which is Calc 1. But that's the fundamental idea of Calc 2 is all this integration stuff. And I noted that you should look at this example they gave you. This is sort of the classic example that breaks things. This is the Dirichlet function. It is a strange function. It's defined to be 0 if the input is rational and 1 if the input is irrational. And what this does is it creates, because of the way the real numbers operate and the density of irrationals versus rationals, you end up with infinitely many jumps. You can't even graph the picture because it's just infinitely many times on any interval, no matter how small. There'll be infinitely many times it's 0 and infinitely many times it's 1. And so the key feature of integration is not just that the norm of the partition goes to 0, but up here on the function, the max and min value need to converge to one another. And the actual value is in between. There's a sandwich going on here, sandwich theorem of limits. And the idea is that you could pick C sub k's such that your approximation is less than the area, and you could pick C sub k's such that your approximation is bigger than the area, but then all of those approximations converge to one another, and the area is always trapped in between. But the key to that is that the max and min values, as those partitions squeeze in on any given subinterval, the max and min come together. So on a nice, well-behaved curve, if this is my subinterval, here's a max, here's a min, or excuse me, there's a max, there's a min. As I squeeze this in to smaller intervals, it's a different min and a different max. But that max and min are going to converge to one another. The min value creates an area less than what's under the curve. And the max value creates an area that's more than what's under the curve. And so as that bigger rectangle and smaller rectangle come together, the actual area is trapped in between. That's the essence of what makes an integral converge to the area. This thing does not, because no matter what you do, every subinterval is going to have all these infinitely many jumpings up and down. And so the min's always going to be 0, and the max is always going to be 1, and they don't ever approach one another. I can't even draw a picture because it's infinitely many dots of zeros and ones. It's just, when you filled it in with a computer, all you would see was just a line up here and a line down here. But there actually is this infinite amount of jump discontinuity there. So that's why when you look in the text, it says that we're OK as long as there's finitely many jump discontinuities. So it could jump, but it can't jump in this crazy infinitely many jumps sort of way. Now, the nice thing for us is all the functions we deal with on a normal basis are only going to have finitely many jump discontinuities or possibly a asymptote. That's a whole separate issue. We'll talk about that later. But so go back to chapter 5 where they're first developing the integral. I think maybe we rushed through that in Calc 1 because we're kind of in a rush to get done. So take some time and make sure you understand the difference, why this is a problem. This actually creates a whole branch of calculus. We define a whole different kind of integral to take care of stuff like this. There's other integrals besides the Riemann integral. So if you're interested in getting a degree in mathematics, you can investigate this further. But yeah, go back and read that and understand that it's not guaranteed that the Riemann sum will converge to that area in between. So, yeah, just be careful. The understanding that you have right now might be a little bit superficial, so we're trying to kind of dig a little bit deeper as to what's going on and understand this a little bit more mathematically than maybe we did on the first pass in Calc 1.